Welcome, I'm Flora, and today I'm going to be talking about mapping the impact of flooding on subsequent flood risk for the River Tweed and investigating changes in the discharge and inundation extent relationship. So the key research questions and research aims for this project are, firstly, how does severe flooding morphologically change the River Tweed? And to answer this, I would have to assess the changes in riverbed elevation and map the areas of deposition and erosion which have taken place as a result of flooding. And then secondly, what is the impact of morphological change in subsequent floods? And to answer this question, hydraulic flow models would be created for based upon the river channel morphology before and after flooding, and river discharge input into these models to produce probabilistic maps for these results. And the third question is, do tipping points exist in the flow and inundation relationship, and do they change? And to answer this, the relationship between the input discharge and the output inundation extent would be investigated to see if thresholds exist. So these research questions were heavily influenced by several papers by Klett, Feynman, and Beavers, which explained how changes in the peak flow of rivers can lead the river to morphologically respond. And this morphological response of areas of erosion and deposition, which changes the river topography, can change the conveyance capacity of the river. And this has been shown to be more influential on the inundation extent of flood than changes in river discharge by a paper by Guan in 2016. Changes in topographic controls were shown to create tipping points in the relationship between the river discharge and the inundation extent of the flood. These tipping points can be explored further using a probabilistic approach, which this project will do. Berman also identified there are many sources of uncertainty in flood modelling, three of which were floodplain topography and the cross sections of the river, catchment change, and climate change. And more recently, it has become apparent that these sources of uncertainty need to be communicated further in order to improve flood management and policy change. So there's a lot of motivation behind reducing these uncertainties and their influence in flood modelling. This is because we are constantly trying to assess and therefore predict flood risk, as flooding is widespread and destructive globally. These tipping points noted by Beavers would be very useful for planning and policy change. This is because flood risk is mostly dependent on the inundation depth, which has been shown to be impacted by the morphological river changes during extreme flooding. The image on the right, the figure shows the output maps from a study in 2018 by Klett, which shows how there are 134 catchments considered hydrohazard hotspots. And these hydrohazard hotspots are a combination of regions where there's a combination of changes in flood and drought characteristics expected in the future. And as can be seen, one of them is Berwick-upon-Tweed, just south of the Anglo-Scottish border on the River Tweed. So this hydrohazard hotspot was selected as the study area for several reasons. Firstly, there's a lot of motivation for understanding flood risk in this area, as the gravel bed river experienced peak flows during 2016 and there was significant flood damage. Most of the postcodes are considered high risk in the area, with some being considered medium risk, as can be seen by the figure on the left. And also because near the coast there have been high levels of deposition noted, and this could be linked to the capacity of the river, which was explained earlier, which could increase the flood risk. But this study area was also chosen because of the available data for the region. So in order to assess the morphological change of the river, there needs to be high resolution elevation data and to be able to properly assess the topography of the river. This was actually a bit of an issue at first with this project, because accessing high resolution LiDAR data within a small time frame was proved quite difficult. However, LiDAR data at 1 meter resolution exists for 2015 and 2017 for this 5 kilometre stretch of the river near the coast, and that can be accessed from DEFRA. There is also the presence of daily flow gauge data as well in the region, which made it even more useful for this project. So to properly complete the project, the following methodology will be used. Firstly, the high resolution LiDAR data, as mentioned earlier, for pre and post flood will be used to, the LiDAR tiles will be used to estimate the morphological change of the river channel. And from this LiDAR data, simple steady state 1D hydraulic models will be produced for before and after flooding river channels. Then the river discharge from the 2016 floods will be input into both these hydraulic models and the output compared. So comparing the inundation extent and depth. After this, predicted flows from the future flows hydrology database will be input into both models, and the relationship between discharge and inundation extent explored further, as well as producing probabilistic maps of flood risk for both of them. The figure on the right also shows, on the left, sorry, shows LiDAR, which is light detecting and ranging data, which produces high resolution ground elevation data. And the figure on the right of that shows how the types of river cross sections which are used to produce a 1D representation of flow for hydraulic modelling. So these three figures show the first stage of the methodology, which is using the 1 meter resolution LiDAR data from 2015 and 2017 for this section of the river to produce what is called as a DOD, or so it's a difference of digital elevation model between the years. So the different colours show how the changes in elevation between the 2 years selected. And this graph here on the right shows a cross-section of the river, and the purple line shows how the elevation has changed, identifying areas of erosion and deposition, which can show if the flood conditions were cleaning or depositing, which basically says if there was more erosion or deposition occurring or neither. So the next stage of the project would be hydraulic modelling. And this is using HECRAS, which is a simple steady state 1D flow model. Hydraulic modelling was chosen because the data can be easily manipulated and the input data changed so that the output can be properly investigated and the impact of the input data fully understood. So the channel morphology and the discharge, for example, are the input data. A 2D model was not chosen, as studies have shown that the 1D model assumption can be made, which represents floodplains as a series of cross sections extracted from the DMs. For this part of the methodology, flow data, river geometry, Manning's roughness coefficients, and different boundary conditions will be required. From these hydraulic models, mapping of the area of the floodplain is expected to be covered during the flood, and the flood depth and the 2016 peak flows can be created. This will be useful in comparing the impact, to assess the impact of morphological change on river flooding. So the probabilistic inundation maps will be used.